Hello friends, welcome back to the Tristos channel. I'm Dr. Tristos. In the previous videos we covered downloading and installing Zilog's Development System. That probably not only placed an icon on your desktop, but one here on your Start Programs menu. ZDS II, eZ80 Acclaim 5.3.5 was the version that I had downloaded and installed. So if we go ahead and launch that, as I stated in my previous video, I've gotten this message for some time when I launch ZDS. It seems to always have some quirk or another. Instead of chasing after trying to fix all of them, I just tell it okay, everything works fine. So, in this video, I thought we would load and compile a sample video. The ZDS comes with some sample projects, and under Quick Start, under Open Projects, Quick Start, and these are just the samples that came with ZDS. I go to the bottom for Simulator. And why do we use Simulator? I told you that we have a simulator for the eZ80 built in the software here in the development system. So this bottom routine simulator it's a sample program that will run in the simulator. It's because all it does is print a hello world anyway. So we will just open the simulator. Everyone should have this same program. This is a C program. I want to point out that TrisOS and all of its work and Tristos currently is all done in assembly language. So I'm going to demo the C compiler. However, all the software that we're writing it for TrisOS and Tristos will be done in assembler. So I'm going to run and compile this pardon me, and show you how we can open the UART viewer. So at the top under view, it's running now. I clicked. Let me stop and do this again. This one down arrow will compile and go. If we look under settings, project settings, this is already set up in the project. Under our debugger section, the debug tool is set to simulator. So this means it's not going to look for an external cable, an external piece of hardware, and try to download this compiled code to that external hardware. No, it's going to run it in a simulator inside your PC. So that's fine. That's exactly what we want. If we look at the top, we have debug windows. They're shaded out right now because the program is not running, but we can see down here one of them is simulated UART. We're going to, if I click this go, the down arrow go, it means compile, download, and go. Well, we just said we don't have external hardware attached, so it's going to download it into the simulator and go. It's that quick. It's done. Down here we have the output pane that tells us connected to the target simulator. Well, the target simulator is simulator, so it's always available. If this was hardware, if we were doing an external piece of hardware, it would report that hardware here. Here we can see we're starting a debug session and the loading the files that it did to do the compilation and come up with a checksum on this output file. This is the checksum, and not that I've ever used that, but anyway, it's now running. If we look up here under View, our debug windows are all available. Simulated output is highlighted, and right here, UART 0. Let's switch to UART 1. There's nothing, because we did not write to UART 1. We wrote Hello World to UART 0. And we have some extra zeros in here and in the hello message, but that's okay. We can switch these back, and this will show you that the file we are compiling here is what is displayed the message in the simulated output here. So we have simulated output for both UARTs. We need to stop the debugger because this one was running. Even though we changed the source code, the program from its last compile was still running. We're going to click compile and go. It wants to know if we want to rebuild the project. Yes. New checksum. It's running, and we can see it's already running, and as we can see, hello has been changed. We will get more into this later, but the project settings is a very critical part of the project. Configures memory, CPU, speed, how the compilers act, what they do, where their output is sent to. Over here, we can. I never use the printing facility. I never use the ZDS system to edit my source code. I can show you an example. All of the source code for TrisOS and TrisDOS is in assembler, and I use these in Notepad to edit all of these files. So we'll just take a quick look down here. Here's the decimal to hex routine. This converts a decimal number pointed to, I believe, by the H&L register pair when you enter this routine. It converts it to hexadecimal. So, but the point is, all of these are edited, and we use Notepad. And the ZDS system reads those source files fine. For very small projects like this, it might be suitable to use the editor that's built in the ZDS workpad area right here. But if I wanted to edit this same file, with Notepad, I would close it in the ZDS and go and open my source code with Notepad. Here is where the ZDS knows what files is a part of the project. Console.h, quickstart.h, standard IO. We could add files to the project, add files that we create with Notepad. The only thing we need to do is if we were to create a new file in Notepad, we need to save that as .s instead of .txt for source. So it's a .s file. But we'll get into that. We'll be doing some examples. So yeah, then we can close our project. That closes the debugger and the simulator. The development system is still open, but we could open another sample project or start a new project ourselves. And we would do that here by starting new project. Under the new project, we'd want to know the directory you would want to store your files. Now, I guess I should probably create a new folder, and we'll call it YouTube. And we can keep different sample files that we do on our YouTube channel. We'll keep them in this folder. And we'll call our project first YouTube project. And if you'll notice here, it's going to save that with the extension of ZDS PROJ. Zilog Development System project, I guess. Here, I'll be doing assembly language project. Now again, all of TrisOS and TrisDOS is written in assembler. eZ80 acclaim, that is true. It also does, there's other eZ80 chips, but you always want the acclaim. From here, you'll select your CPU. As I told you, I support F91, F92, and the operating system self-configures to the chip you have. But for writing end-user code and we do not support the F93 at this point, but for all practical purposes, just select F91. And we want to build executables. There's also static library. I don't use that. We can't get into that later. We press continue, and it wants to know. Now, ultimately, I'll be using an eZ80 development platform, F91 RAM. I always write to RAM. We'll be doing this a million times. We don't want to be reading and writing our flash all the time during development. We're going to use our RAM memory. Besides, TrisOS and TrisDOS only runs in RAM. That being said, I thought I already had maybe not. Let's take a look at the setup for this target tool. We do not want to start in the ADL mode. If you're coming over from the Z80 world, you do not want to be in ADL. ADL will be running in 24-bit addressing. You will want to uncheck this, starting in ADL. It's your choice if you want to enable or disable the eMac RAM and the internal data memory RAM. I leave them enabled. We do not use the eMac RAM. I don't use either one of them, but I do leave them enabled. Everything else, we're running at 50 megahertz since we selected the F91. We can just tell this okay and take it at its defaults. And here we can see click finish, and we're done. We now have a project file created and set up with the settings that we just programmed. Now, there's several fields here, and I will try to cover each one in general, and we'll start off with general. This is the CPU we set up when we first created this project. Now, when we build, show warnings. Warning messages are not necessarily fatal. It depends on how you treat them and what they are. It's best if we, I leave these default settings the way they are. Show warnings, generate the debug, and we do not ignore the case of symbols. Let's leave it the same. As we can see, it's under Quick Start YouTube. If you remember, we created a file folder called YouTube. And next we have our assembler. Now here, since we have not really started building our project yet, if we did have files and we wanted to include those files, there's a couple of different ways files get included. You can use the include statement in your source code to pull in additional files to be assembled or compiled in the code in line. Or here you can declare them externally, and you can also define symbols externally. So I could define a symbol inside my assembly saying Daniel equate hex 80. And maybe I don't want to, maybe I want to be able to universally change that outside of the assembler without editing my source code. Every time I build the project, maybe I want to make many different values for that, for different versions of the project. I could do that here under defines. And we can already see here that, for example, simulate is a flag to the assembler. And it's already telling the assembler that simulate is on, because as you know, when we run our program, it is just running in the simulator. If we were to change that, this would go away. That this is an external declarations to the assembler, external defines, and external directories, places to look, files. Generate a listing file, and this LST file will be in the I'm kind of old-fashioned, will be in the directory of your output. I'm kind of old-fashioned. I still use a 132 column printer, 66 lines on a page. We do not want jump optimization, because what that will do is if you have a jump instruction or a jump relative, and the compiler can automatically improve, save 1 byte or 2 by changing a physical jump to a relative, it will do that automatically. For God's sake, it's the last thing we want to happen, because when you're writing assembler, we may need that jump instruction, and we know the exact length of it, and we've planned on that in our code. And if you was to save 1 byte, it would turn the world upside down. So we don't want, under advanced, we don't want any optimization taking place. We'll do our own optimizing. Our linker, here again, you can put additional directives into the linker. Object libraries, if you have other files, object code files that you want to include that will resolve external references, external global references. That's what we would do that here with the object library. This is where we would include those files. Our address space lays out how it's going to see the system right now. We'll get more into this more later. Right now, luckily, we can take it at its defaults for our sample projects. Treat all warnings as fatal. I recommend this because there's times when you could get a warning that the assembler will let it go through, but especially when you're writing assembler code, it can mean the whole world is wrong. So you need to know about any warnings. If they're fatal, it's not going to continue. It's going to let you know that you have a fatal error. So we always want to segment overlaps. What it's talking about here is when you write a segment of code, saying it will lay in a certain address space, and then you assemble with that another section of code, and part of it overlaps or maybe completely replaces the other segment. If there's an overlap, they both can't occupy the same place at the same time. So we'll get a warning. If you're basically what is happening there is two segments are trying to use the same location in memory. And yes, of course, we want to know about that. Our output, we can come down here and put in our output. As we can see, we're doing the debug here. We can either do debug or release. If we change this to release, this is going to change the output directory names from the release under our quick start YouTube, release, first YouTube. Remember we told we was going to call it first YouTube project. All right, so if we're still, this allows you, if you're running projects and maybe more than one person is working on it, when you're developing code, you can do that here in the debug. And when you have it working, you can move that up to release and then compile, and it'll put all of your output files in a new directory called /release instead of /debug. People knows when they look in the release folder that, well, you've released that, it's working, or you yourself know that was the last version that was working. But otherwise, you do your development and debug. Here, I don't really use the executable formats to develop TristOS and TristOS. You'll see that we save our binary core image files a little differently. Yes, we wanted to generate a map file. I'll be honest with you, the map files for an assembly language programmer, this entire development system was really written with C development in mind. It is not the kind of assembler that we would think of that a lot of the Z80 programmers will come over from, where it builds more definitive symbol tables and output reports, and this is just not geared that way. It's geared more towards C development and a different approach to programming. Is there anything else? Oh, our debugger, we've already covered that. That's where we plugged in down here who we are, which development platform, RAM, but right now we're just doing things under simulator. That will get you up and running. Get a project here ready to accept source code. And in this case, we selected that we would be doing assembly only project. So yeah, let's next video or so, maybe we can start loading some source code and do a sample program and output to the UART. Thank you for watching, and I hope to see you back here again on the Dr. TristOS channel. And if you have any questions or comments, be sure to post them. Thank you.